Welcome everybody. Today's lesson number 6. It's kind of an overview session, I think. So it's kind of wrapping up a lot of stuff of the previous sessions, and we can discuss like if we are stuck with some concepts or if everyone is on the same page. I prepared a couple of slides and I suggest we just run through them and stop me whenever for discussions. And we do our usual routine, right? So I don't know if we still need to introduce our study group, but I mean, briefly, we're doing the ML1. That's still based on Fast.ai 0.7. So for people that are doing the live version 3 deep learning one, we are on the old version of the library for this course. So be aware. Yeah, and we planned on doing a couple of homeworks or side projects. I'm not sure how people are doing there. I'm struggling a bit because of the second course I'm doing. But anyway, we can discuss stuff if people have results. And in the end, then obviously next steps, resources, all the usual stuff. You know us by now. Just reach out on Slack if you want to do some kind of a mini presentation or anything. Just any one of us. Someone is always online. And right, study group. Yeah, weekly sessions. So I think we kind of decided to keep it on the weekly one, even though people are kind of getting a bit, not really behind, but tired, especially people doing the deep learning stuff as well. But for the moment, I think we're gonna keep it like that if there's no big objection to that. Right, today, as I said, it's a bit of a different lesson, at least I have the feeling, because he was spending quite some time explaining his kind of ML philosophy or kind of general approach, which actually was quite kind of interesting to hear that to me. And then the second half of the lesson is the big one, is basically a recap of all kinds of interpretability tools that we have now and why they are good. So in the slides, you'll find a couple of links again, and we'll share it in the Slack channel. So if you need links to the kernel notebooks or setup instructions, all this kind of stuff, it's in the slides, which we will circulate. So I'm skipping over that, like object if I need to spend time on this stuff, but I'll just walk through if no one is stopping me. So right, I kind of peppered it with a couple of citations from this actual lecture, because I think they were quite neat, like this hint that most managers build all kinds of tables and charts without any kind of machine learning or kind of intelligence behind that. And that's a big drawback, or a big chance to actually improve this stuff with our tools. And the problem is that they most often just take data from their databases and have a one-to-one chart of some dependency or some links that they think should be there, but it's basically no way of knowing if that's really true if you don't really look into the feature importance, for instance. And that's why random forests, even though they're kind of a simple technique, are still super useful. At least that's what I took from his kind of statement.
Yeah, I was thinking again why the random forest, the question, and then he also mentioned other tools at the end of the lecture, like gradient boosting and the neural networks.
Yeah.
And then he also mentioned why random forest is not good for some problems. So that kind of answered my question, which I had like initially.
Yeah, so I think like in one of the last ones, I have it that basically don't use them to extrapolate, like never. And yeah, the others are a bit better, but in the end, you might want to switch to neural nets. Right, so I mean, I kind of do that kind of quickly, I guess. The Drivetrain Approach, that's like one of his links. It's basically one of his publications or some kind of a online publication. And that's basically the general train of thought that he uses, like how he structures his projects and what to think about, right? And there's like 4 components to them. He calls it the Drivetrain Approach. First, and the most important one is basically to actually define a clear objective. And he says it's not to define, okay, I want to improve some score of a model, but the actual business kind of objective, what should be improved or what's the concern. And then everything falls into place depending on this kind of objective. So it's what should be the outcome of the model exercise. Why do we do that, and what can be improved? And this can be improved thingy is basically the second one. It's the levers. So it's basically, okay, what can we actually realistically do about this whole problem? Like some stuff might be totally out of our own control, so there's no point sweating about it if there's no way we can actually tackle something. It's basically the objectives that the company or we can control, basically stuff that we can manipulate or modify or dig into that could actually change the outcome. And then the next step that's linked to that is then the data. So basically, what data do we have? Could we get more data? Like, that's why we probably want to do feature importance right in front of the whole exercise, figuring out if there's anything that would be super helpful for our understanding if we have more of it. So identifying basically the most important features. And only in the very end is basically the models. And then potentially the predictive modeling stuff that is really like the fancy thing to do. And basically, yeah, that's the whole point, that you need to think about the overall goal, what you can actually manipulate, what's the data that describes that, and then in the end you can design your tool chain, building a super deep neural net or doing whatever, and actually optimizing model outcomes and stuff like that. And yeah, I kind of mentioned that basically why these random forest or these simple tools are actually useful. They can actually tell us, okay, what can we pull? What's the handle on the problem? Can we like just understand the problem better? So he says it's kind of a random forest are at the intersection to answer some of these questions. So they're kind of central to understanding what's going on, or can be. Right. And then he goes on, I'm not sure if we should dive into that. It's basically kind of a conceptual thinking about, okay, what kind of applications are there in business? Like he splits them into like horizontal approaches, applications they are basically applicable to almost all kind of businesses, independent of the domain. And he goes into some of these examples. I don't know if you want to talk about that. Otherwise, I just skip over, and that there are vertical applications, and they are basically domain specific, which are certain to a certain domain, and then they're probably more specialized or have certain criteria, like in healthcare, whatever. Maybe the uncertainty rate there is much more important because it's a matter of life and death instead of some other topic. I don't know if someone wants to chip in here. I kind of skipped over that part a bit.
I was just going to say, this was, I thought, the most important part of the lecture was, I mean, he just kind of flashed this on the screen, but if you actually like pause the video and read through some things, it's just a really good resource for brainstorming ideas.
Yeah, it's good for getting ideas, like what can be done, or like where can ML be applied, like the kind of fields or topics. That's true. You want to discuss it? Should we stick to it a bit, or you?
I mean, I just wanted to just call out that it's worth pausing the video when he provides this, and just,
yeah,
it's a good brainstorming tool.
There was super much stuff here anyway. So, I mean, life science, biomarkers, drug discovery, analyzing study results, a lot of stuff. So should I continue, or you want to?
Oh, go ahead.
Okay. So yeah, plenty of fields where you can apply this stuff, potentially. So right, so basically the the topic then was basically about using random forest for interpreting what's going on, like as a screening method, really to understand what's happening. And he runs through a couple of them, and they're kind of a collection of the previous lessons. So the first one is the confidence based on the tree variance. Then there's two types of feature importance measures. Partial dependence, what I found most interesting to me, to be honest. The tree interpreter and waterfall chart, which is kind of the same topic. And just prepared a couple of slides where we can hop through, I guess.
Christian, just a question. Sorry, I was on mute and I was trying to talk. So,
That's right.
you know, the first thing was around the prediction model, and then the second thing was around how you can actually simulate different options, and then after, you know, the next step after that was to try and optimize based on the simulation. What wasn't so obvious to me was, how do you actually simulate the different options available to you? Because I think that's, so my understanding from lesson 6 was what he added to he added was, forget, okay, you've got the ability to predict, which is where most people kind of stop. But then you were saying you can go on and simulate, and then after you simulate it, you can optimize to whatever your objective is. My question is, how do you get that simulation data so that you can figure out what the different options are? And it wasn't clear to me how you can actually provide those different options with the view to then optimizing it.
Not 100% sure, but I would imagine, for instance, if you understand these kind of levers, that you kind of come up with certain actionable things you want to do, and you predict what they would cause. That's how I understood it. So basically, you make up like what if scenarios based on, okay, what could actually be changed in the business, and then you evaluate them. Or are we talking something else? Do you mean something else?
Yeah, I do mean that. But okay, when you do that what if analysis, right, how do you then know what the, so for example, you know, in the one you gave about insurance, right? Yeah. If you make some change, for example, you change someone's insurance premium, how do you then know to what extent? So when, as part of that what if analysis, you're doing a whole lot of simulations, right, to see how someone's going to respond to that. The bit that wasn't clear to me was, how do you know the responses for those different options? Because you don't have that information.
Anyone want to jump in?
I think we do have, like, so there's in a one of the parameters would be the insurance premium. So then we kind of build our model with that, and then we can change that, right? And then we can see, I'm just thinking aloud, we can see how changing that parameter would affect the other, maybe. Maybe I'm wrong.
Yeah, I don't really have a good answer either. So I don't know if someone wants to try.
Well, it would seem to be awfully strange that you would put together a model that you would have no way of verifying it. Don't you think? Say, as an example, you want to change the behavior of your customers by purchasing more insurance. It would be strange that you would put together a model of prediction and then not have any means to verify if it works or not.
But couldn't you just relate that from your kind of total database, that if you cluster like certain customers with certain contracts, compositions or whatever, how like, I mean, I know what you mean, that you can't really predict if they will leave or change their behavior, but maybe you could, I don't know.
Well, you know, in that particular narrow case, the way to know if it's working or not, you know, I'm assuming, say that you're advertising, you're spending X amount of dollars in advertising.
Yeah.
Then are you getting on the new sales are you attracting the people that you hope to stimulate to buy your product? The
Yeah.
same age group and income and whatever segment of your market that you're trying to grow in.
It's kind of a slow and expensive process, though, potentially.
Well, you know, sometimes you have to bite the bullet too.
Yeah.
Because it comes down to change. And everybody has to change. So the question is where can we find to change in the best way to get the best effect that we're looking for?
Yeah, I mean, what I was thinking about is like at least for retail, online retail, people would just do A/B modeling, right? Redirect a couple of customers to a different model, and then see the click-through rates or whatever happens, and then you can have a relative measure like how effective that was.
Well, yes,
yeah.
that would be one way of approaching it.
Yeah.
Yeah, I guess so.
But in a medical environment, you might have to count how many people who die.
Yeah.
Yeah, in medical environment, you have the clinical trials and stuff like that. So they also do test new drugs or new stuff. So they have ways on that as well. But I guess so. I guess you kind of try if that works. You're right. You have to validate it if that really works. You don't want to change that for good, like just based on the model. It's a good point.
Okay. Where were we? Right. So I don't know. I mean, I guess we just flick through the individual methods. So the first one was the tree variance. So basically, normally when we do the prediction on the random forest, we just get the average. And here we would actually collect the standard deviation of these prediction results. And then we have a measure of how certain or uncertain we are about individual features or groups of them. That was the example that you could also group and say, okay, for this group, we are more certain than for others, and basically identify if we have variance in there. And it's done basically by your individual row or groups. Then feature importance, that was noteworthy because basically he mentioned it a couple of times. That's basically the second thing you do after building the random forest. That's why I put the quote there. That's basically, okay, you have your random forest of all features and stuff, and then immediately afterwards you should actually try to find out what are the important features and then concentrate on them. And I found that quite interesting that he was underlining that a couple of times, basically forget about feature number 3 or 4, just go for the ones, if there's a big difference in the magnitude, just go for the big one and forget about everything else. And once you know what's going on with the first one, if it's really super important or if it's just a data leak, like here had the mention of one student there, that it was basically just a different version of its actual target, so it was not really independent feature at all. So that's super important. Therefore, basically do that right in the beginning. And there's 2 types, and the first one that was, I think, introduced quite early in the series, right? There was pick one. Oops, series coming up. No. You pick one feature and scramble basically the order in your data frame, right? So you don't delete it and train a new random forest, but you just rip out the correlation towards the actual observation, and therefore you still retain the distribution. So you don't modify the data per se, you just break the link to the observations. And that should basically, the change you see towards your previous prediction will give you a measure of how important that was, right? If it was super important, then your prediction should change a lot. If it's minor, you should see little change. And I guess one student was asking about, okay, about the units, if there's any meaning to the units, but in the end he mentioned it's basically just the relative feature importance, right? You rank them and sort them by their importance, and you concentrate on the big ones, basically.
Well, is there an objective way of determining what's more important? Is there a number that we're looking for, or is it, like our table there, there's one variable that's 1.17 something. So that's
I think it's
what to focus on.
The one with the biggest difference to the full random forest prediction, basically. And I think he actually mentioned he wouldn't even know about units because it's relative feature importance. He would always pick the top one, basically. And then there was a second one, but I would need some input of you guys. This type 2, that's basically giving you the same outcome, but it's a different method. It's the tree interpretation, but not for a single row, but for every row, and you add them up. I don't know, like if one would pick type 1 over type 2, I have no idea. I think he mentioned in the lesson that they are targeting it from different angles, but they're just the same in the outcome. So,
can you talk further about type 2? I didn't.
I had to look up the recording again as well. I found it in one of the lecture notes, basically, and I thought, okay, I kind of missed that. So it's in 1 hour and 4 in the video if you want to jump in later. I don't think it's super important. I think the shuffle one was mentioned in the beginning and he concentrated on that. So I would just go with that one anyway. Seems logical. Like
it doesn't make sense to me that evaluating every row would give you a feature importance. I don't see how that.
Yeah, that's why I asked if anyone wants to chip in, because I wasn't too sure about it and was a bit late to really investigate.
Okay, thanks.
All right. And yeah, basically you just, I mean, you do your sorted plot of feature importance, then you immediately see if you have 1 or 2 of them, same as looking at the numbers. That's super important, and then you concentrate on the first couple of ones that actually matter and forget about all the others. And if you identify, I guess, that some of them are actually, yeah, just bad data because they encapsulate something of the target variable, you rip them out, do it again, and then maybe there's other features that are suddenly important, right? I think we had it in one of the lectures in the beginning where we excluded one and then it changed quite a bit. Now this one, that was, to be honest, new to me and really intriguing. It's the partial dependence. So it's basically a method to figure out the true dependence of a variable. So basically, you kind of strip out, or you try to rip out correlations or interdependencies, and you just concentrate on the actual contribution of this one feature. And the way you do it is basically that you pick a row and then freeze like a feature. You hard code a feature, or not a row. You take the thing and set the feature to, I don't know, this example was the years made, and you set it to 1960. So basically it's now constant for all predictions, and therefore you see you get one data point, and the lines in the plot are basically the individual rows. And basically if you look at the lines individually, you might identify that there's clusters of observations that behave differently. If they all fall into the same kind of channel, then they're comparable. But he had an example of a different mate And then this one was basically had different trajectories, and therefore you could identify different behaviors for different parts of your data. Basically, if they all follow the same kind of trend or line, then they're more homogeneous, I guess. Yeah, I don't know. Anyone wants to jump in here, explain that a bit better than me?
Well, I just want to say that amazes me. I didn't understand that's what he was trying to do. And I think that's amazing because when you have a large amount of data, there'll be, what would you call them? Relationships that are buried in the data.
Yeah.
And this is an opportunity to see those separate relationships, like
yeah. I didn't really play around with it a lot, but I never really used that, or I've seen that before the lecture, so I was really interesting.
This must be what was meant by the type 2 on the previous slide.
All right. Well, should rewatch. Yeah, but yeah, that's kind of interesting. I mean, did any one of you actually try that on a different data set and see if you see interesting stuff? Because I mean, I planned on doing that on the taxi stuff, but I was so busy with the deep learning things that there wasn't any progress. But that's the one I really wanted to try to see if there's autocorrelations or other stuff going on that you can pull apart. Anyone?
So I didn't do any other data. I'm just trying to still more understand this. So the way you do it, you take the year made column parameter, and then you change that to a year like 1960. And so then you get and then you put that through, because you don't calculate random, you don't get the random you don't do the,
you don't train again. No, that's for all
right?
methods. You don't train again.
Oh yeah. Right. Yeah, that's right. Okay, yeah, that makes sense. Yeah. So then you put through a trained forest, and then you get a number.
Yeah.
And you do it again and again.
So basically, to get one line, as far as understood, you pick a row, you inject 1960, for instance, you get a data point, you inject 1961, you get the second one, and then you make up this kind of a trajectory. And then you do that basically for all observations, and you get this kind of funnel of lines. And if you take the median over time, then you would, for all time steps, you would get the yellowish line and then the overall thing. But he mentions, and you can see it here as well, there's probably a couple of these lines going at the top that are a different kind of cluster. So just taking the mean might obscure some actual meaning in the data, right? So you should always, I guess, plot them individually if they're not millions or whatever, right? Or you could probably subsample and have a look at the individual ones and see if they all behave the same. And I guess you would do that for your top 3 or 5 features that you identified, right? Because obviously you don't want to do that for all variables, but for the important ones.
Well, how would you know there is a partial dependence? Where would it jump out at you in the data, in your example?
Yeah, so he showed that graph where there was a year made and sale price, and it was in the sale price on average was increasing, but then there was a couple of years when it was going down.
Oh,
so
yeah.
That was kind of looked like, yeah.
Yeah, if you remember the lecture, there was
and then
I think there was 1990s or something. There was like a downtrend in the sales data, a brief one, like of 5 or 7 years. So it was kind of monotonically increasing up to this point, and then a short kind of dent, and then going up again. And that's not showing up here. So it's not due to this variable that we're inspecting here, basically. So it's, I guess, by exclusion that you figure out, okay, there must be some other effects not captured in your variable.
I guess that he chooses this specific one because in the feature importance, he sees that it is important, no? So he wants to plot only the year made against the price, which is the final target.
Yeah.
to see the direct relation, no? And then he sees what you mentioned, this going down in certain years.
Yeah.
He wants to understand because that it looks like it's the direct relation between the year made and the final price, but actually there are other things influencing. So with this technique, no, he can uncover what really is the relation.
And I mean, that was actually kind of a convincing argument. Like if you pick any kind of data set, right, and just pick two variables and plot them, very seldom you just get a direct one-to-one relationship. You often have other contributions going on. And if you don't investigate this kind of stuff with a multivariate model or like stuff like this, you just don't describe it like features that are just not there. So that was kind of intriguing, but I didn't really find any application myself on a different project yet where I wanted to use it.
I guess that the conclusion from this will be that there is not this going down relation with the year. Actually, maybe there were some other features that were changing and that was dragging the price down.
Yeah.
Like, I don't know, in those times, maybe they use smaller machines. I don't know. But it was not the year, it was something else, no?
Yeah, I guess his example was, I can't remember, if like looking at this plot, you might assume that they should stop selling this or buying it, or I don't know what the business case was, because it's not profitable or it's dangerous because it's going down. And here you can say, okay, no, but this data was actually skewed or affected by something else and not by their kind of business logic. So yeah, that was kind of
also interesting.
It's interesting.
Yeah. What's interesting also is like, so if that trend between the year made and sale price was as expected, I guess we wouldn't look at that some more justification why that happened. It's only when we question things then we kind of go deeper. So and then only because our assumption is that with the year the price would increase. So then we kind of dig deeper and understand why, but we never question when it's when the trend is as we expect. That's kind of it's not only here, but it's everywhere. Maybe that's a bit on a tangent.
Okay. Moving on.
Sorry, it's because maybe before we move on.
Yeah.
When he clustered these lines, because I see that you are going to the next thing.
Yeah, sure.
There is a point made that he clusters this bunch of lines. I really didn't get why he does that. I don't know if any of you.
Yeah, I think I can take a jump at that. So basically, I think the clustering was to make sure that you don't average out features that behave differently. Like in this plot, if you imagine that the top, I don't know, probably 10 lines, they follow a different kind of trajectory. So you think, okay, maybe if he clusters them based on their similarity, then you see different features in your data. And if you just take the median, like here in this plot, you ignore that because you can check basically if there's patterns.
Okay.
In there, that's the clustering.
Okay.
Yeah.
Thanks.
Right. Okay, this one probably would need some input as well because I forgot about it and then just chucked it in like 5 minutes before we started. So basically, the tree interpreter, we pick a row, we call this, I think it's an external module, right? It was import tree interpreter. And we give it the model and the row, and it spits out basically all the components of the prediction. So basically you get 3 return values. The prediction itself, the bias, which is kind of the starting offset, I think. That's in there for all features. And then the contribution. And they basically, you can kind of visualize them using this waterfall chart. And you basically, I think you start with a bias in the beginning, right? That's the big one, and then you just build them up. And yeah, I don't really know, like, how is that super different to the previous ones, apart from that you can compare the bias versus the actual contributions. I'm not sure how that is more important or different than the previous methods, but maybe someone has a point there.
Actually, I have more questions than contribution to this,
okay.
Well, responding to your question, I think that here you can see how each feature is affecting the estimation. So in this example, you see that the coupler takes a bit high the price, then closure gets it a bit down. I guess to understand a bit what is making it more expensive or less expensive. But so my question about this is that it looks like it does it with a single tree, no? So that no, because the only way this comes from this tree interpreter that takes the tree, gives you the bias, and then there is the division in a feature. If it's above some value, you take this.
Yeah, it's for a single observation.
So, but not only a single observation, it's also a single tree, no? So a single row and a single tree. This is only one tree.
I don't think a single tree, because if you feed in the model, so I would assume it's all the trees.
But for each tree has its own first feature as the first one to divide, for example. So it cannot really be all the trees. I mean, even some features are not even in all the trees. So that's what that here is where it comes my question.
Yeah,
no?
I have to pass on that. I would need someone else to comment. I can't.
Yeah, I think similar here would be that we don't do a tree classifier. We just use the existing tree that we've built, right? The existing model that we've built, and then so that model would contain all the trees, I think.
Yeah, but this represents only one path through the tree, or yeah.
But a single tree.
One path through a branch, actually.
But
because
I don't see an option to specify which one.
Well, my confusion is if you went through each row and you did this, because that's what he was doing, through the tree, you'd always see those same things. So what would jump out at you to say this is important or whatever? I mean, that's the piece I'm not getting.
Okay. Anyone else who wants to chip in?
So we have all these wonderful questions.
Yeah, I don't know. I didn't really think that through, to be honest. Yeah.
So, for example, the row that I mean, that one that starts with the bias, and then it splits in two, depending on a variable and a threshold, and then it splits again in two. Mm-hmm. I think that was the tree interpreter, but I'm not sure. He shows it in maybe the second lecture, and then again, I think he showed it in this one. And I think that if you go through that plot, you get this waterfall. No, you start in the bias, you move one, you choose one branch, and then you add or subtract a bit from the final estimation, and so on. But then I think it's a single tree, so I don't know if you have to do it to several to get an insight of what the random forest, gives you. But I don't think it can be the full random forest because of this, because the features for each tree are in different order, because it takes randomly the samples, and I think it's in the random forest that even the feature, every tree sees different features, not all of them.
Yeah.
Maybe this is in the extra, no, how was it? There is one more step above random forest, but I don't remember. Extra trees, or I don't know.
Well, I was wondering, the total is supposed to be the prediction, is that right? Because that's what you with the table.
Yeah.
For me, from a single tree.
Yeah.
But that's great. Let's make this
a branch through the tree.
A single branch, but you take one of the trees of the random forest and you get the prediction from that tree, and for that you follow the branch to get to the
row. Yeah.
Let's make this a homework, huh?
But this could be also average from all trees, right? You can think of like, what average do I get when I split, when I have this group, right?
I mean, the bias, I think, was also the average of the first node.
The bias, yes. The bias,
yeah.
So The bias, I think it's shared between, sorry.
That's right.
The bias, I think it's shared between all the trees because it's just the average of the price. But then, I don't know if this is wrong, what I say, that I think in every tree, the features can be in a different order.
Yeah, that's fine. But then still, you can still take average, right? You can still take the average of all, whatever it was split on the first, second, third, fifth split, you can still take average, right? And an average is still an average. So you can get an average of averages. I'm just thinking aloud again. So it possibly could be all the
Let's try to figure that out. I mean, that would be interesting. Let's read that up. I mean, my gut feeling, to be honest, would be it's the average, because like with this such a generic function call, and you don't specify like the single tree, that doesn't make sense for me that it works like that. That you pass a full model and you get a result, and you can't like get the first one, the last one, anyone.
True.
I assume that's averaging, but would be good to know. Yeah. Let's find out. Okay. I mean, the next one is basically one big topic, I guess. It's basically that random forests cannot extrapolate. And I mean, that's something to be really very wary of. I mean, it's kind of sold as like the super easy first step, but if you're working on some time series prediction stuff, it's just no good. I mean, I didn't really 100% follow the explanation why. I mean, he showed the example of that it's basically all with a linear increase, that like all the future ones are falling to the last known within the training data, that they all kind of fall on this and it just collapses. I mean, the remedies are kind of interesting. I'm not sure if that's like, if you absolutely have to use a random forest that you do that, or if it's actually a feasible method, like this detrending thing. I don't think he mentioned that if that's like kind of a last resort. If you want to use a random forest, that you detrend and then you can still use it on kind of time dependent stuff. But he also basically mentions that even the more sophisticated methods like the GBM, they can handle time series data, but they still can't predict. So for me, the conclusion is, okay, if there's anything about future predictions, forget about these methods and just use neural nets. And I think that was also his kind of conclusion and his outlook, that we're gonna dig into this stuff in the next lessons, and that's basically the motivation to move on into different methods. Right.
What was GBM again?
The gradient boosting, where basically the algorithm homes in on areas that are underrepresented, or I'm not sure, like he picks specific branches and then boosts them and features them.
I don't see how the GBM will help, because what I understand is that with the GBM, you use one tree, for example, you get your estimation and you subtract, how was it? Okay, if you have the training dataset, you have the final value. So you get the error and then you train another tree on that error. So I understood that this is the GBM. I don't know if it's right.
I didn't look into them. I don't know. Okay.
So I wasn't going to say that I don't see how it will help, because this error will also grow if you have a trend in that variable. So, you know,
what he said was basically that they are better for time series data, but not for predicting into the future. So, but yeah.
Yeah.
So don't do it, basically. Right, and that's it for the lesson slides from me. I mean, I don't know. I definitely have to rewatch a couple of them, because I was some of the stuff already faded out of my short-term memory. But for sure, like the partial dependency stuff is super intriguing, and I plan on using that for some complicated data sets also at work. That I want to see if the assumptions that I did previously with multivariate regressions or stuff, or if that's really true, or if that's just artifacts. Any other kind of things you took from the lesson? Anyone? Any major comments? you took out of that?
Yeah, not a major comment, but I'm thinking that the gradient boosting model might work better than the random forest in that it maybe takes care of the detrending automatically because it's looking at residuals. So it probably sees that there's a linear trend and it can remove it or something like that.
I think he mentioned that that it's kind of normalizing or regularizing by itself, yeah, by its kind of concept in a way, yeah.
But did he mention? I didn't listen to this lesson yet, so I apologize for that. But did he mention why neural nets are so much better? To me, it's a mystery. I mean, to me, extrapolation is impossible no matter what you do. So I don't understand why neural nets would be any better at it than
but it's, the example that he gives is excellent to understand the point, because he shows the typical cloud of points that seems to follow a line, and that you can, if you do a linear regression, you get a line, no, that adjusts the best to these points. So if then you take a point that is really far into the future, so in the x-axis, this linear regression will predict it very well because it goes up, no? Instead, a random forest over the last value that you train, it will be flat. That's why, I mean, in the example, you can see it very well.
I think neural nets basically learn model parameters in a way. So
I see. Right. It's because random forest is really a non-parametric fit. And so, but neural network actually has parameters, and they can help you with estimation. I mean, they could build a model that depends on parameters, and then you can estimate in the future. But even so, you have no guarantee that just because your data that you see is linear in the time frame that you're measuring it, you have no guarantee that the linearity extends to the future.
Yeah,
so
for sure.
That's what I mean by extrapolation is really impossible.
Yeah, for sure.
Not only that, the farther it is what you want to predict from your training data, the error will be bigger and bigger also, even if it follows a line.
That's right. Even in a regression solution.
By the way, have you seen that? There was like a last couple of weeks or months from, I think, Facebook, a new time series prediction kind of tool that they were raving about at a conference. I can look it up and put it into Slack. Basically, they solve time series forecasting, whatever. I don't know. It looked totally fancy, but I have no idea. Anyone seen that?
No, I haven't seen it, and I will be interested because what I'm working on is precisely time series forecasting.
I took some notes. I have to look it up. Yeah, cool. I'll put it into Slack.
Great. Yeah, I'd be interested too.
Yeah.
All right. I mean,
well, I have one question.
Go ahead.
Kind of off topic, and that is, where is everybody? Has our new timing alienated some people where they can't make it? Because normally we have double this number of people.
You mean where is everyone location based?
Yeah, we had more people last time, and we changed the timing.
Okay, I missed last time, so I don't know. Yeah, I don't know. But I think
good point. So we sent the emails out to with the new timing well ahead in advance, like last week.
You mean people just didn't realize it, or did we exclude Asia somehow, like time-wise?
Well, there's also Asia and Africa as well, and even Latin America as well.
Yeah, but Africa should be like European time.
Yes. Yeah.
Yeah, so we cannot accommodate everyone. That's for sure. Let's see how this goes next week. Maybe. Yeah,
maybe people didn't realize it. Yeah. But it's on the same time slot like the deep learning one, right?
Yes.
Yeah, it's the same one. Yeah. And then we had more people as well. Yeah.
I have
it's also maybe people.
Yeah, I have a feeling it's people trying to do both, and then it's really tough.
It's a lot, yeah. I was surprised, really. I mean, if you really want to kind of do homeworks for the live course, that it's so much time.
Yeah,
well,
exactly.
We had a lot of people from India, and I just checked that in Mumbai the time right now is 11:18 p.m. So maybe it's too late for them. I don't know.
It's easy.
Well, we could also consider going back an hour, starting up an hour later. I mean, earlier. So we would get the difference.
Yeah, I mean, we can probably ask around. Maybe we ask on the Slack again, or maybe we can actually send out an email, like they should raise if they were excluded because of time, that they should shout out. But I wouldn't want to change it too often. Like, I mean, maybe just figure out what was going on.
Yeah. Well, we should at least give it one more week and see if.
Yeah, exactly.
Yeah, that's true.
And they have I think the Asia, they have their own study group as well. So I think it was yesterday or day before yesterday, I joined for yesterday, I think. So it's not specifically for ML, it's in general.
Okay.
It's an afternoon of their time. So
we should pull them back in with some, I don't know, event.
Well, yeah, it's usually that's what happens with any kind of like course, that we lose people as we go through it, and now we have a couple more, like now have deep learning going on, which is live. So I guess if people have to put priorities, I would imagine that's what I would do. But I think when we start the neural network, that's going to overlap more with the deep learning course. So that's we can kind of Was anyone peeking into the future? I haven't. Like the coming up lessons. Was anyone already watching them? Well, I did watch the lesson about the neural nets for structured data.
Okay.
Yeah, so it's kind of like overlapping more with the deep learning stuff.
Right. We'll see. Was there actually some homework? Because I'm just looking at the last slide here. Well, we have our own homework, figuring out the predict one. Was there a course homework? No, I don't think so.
It didn't mention anything, no.
Oh. Okay, so I know. I mean, as usual, if anyone wants to present, I mean, I still owe you my taxi Jupyter notebook. It's on hold, but it's coming. So maybe it's ready till next week. I don't know. Otherwise, reach out on Slack if you want to share something, discuss something. We don't have to stick slavishly to the lesson. If you have some interesting short thing you want to discuss, just do it. You'll find the links again in the slides to the wiki and everything. Yeah, I think.
Do you mind if I share something real quick?
Yeah, sure. Go ahead.
I just added a link to the chat. I've been working on a project to automate the practice of data wrangling for preparation of data for machine learning. It's still in the early stages, but I recently took it open source, and any feedback or feature requests or anything are always welcome. So it's linked in the chat there.
The Twitter one?
Yeah.
Okay. Taking a look right now.
It's a link to an essay, but I've been blogging about the project throughout. But it's basically a Python class that takes as input some arbitrary structured data set, such as a CSV file or the like, and transforms it into a form directly suitable for the application of machine learning in the framework of your choice, and is kind of it's kind of been something I've been working on for 2 or 3 months now, and just looking for feedback from other people in the industry if it's something that could be of benefit. So
sure, we'll check it out.
I'm not sure what your goal is. Well, it sounds kind of impossible in a way, because it includes images as an example, or I mean, it could be all kinds of weird things.
Well, it's not intended for images or video. It's intended specifically for structured data sets. So stuff that is a single column per feature and single row per observation. And it's not universal. It's intended to simplify the final steps of processing data prior to the application of machine learning. It's certainly not a replacement for feature engineering, but the goal is to move in that direction. So that's kind of where I'm trying to take it. But right now, it's kind of just a final steps of data processing, such as to normalize numerical data and encode categorical data to simplify the application of machine learning.
Okay, we'll check it out.
Yeah.
Anyone else?
So you want to automate Panda, right? In part.
Sorry, I didn't understand that. Were you talking to me?
Yeah, so you want to automate in part Panda, because that's one of the functions of Panda.
I mean, that's the goal is to automate what is largely a manual address for a large part of the data processing work.
Cool.
And yeah, any feedback or suggestions are always welcome.
Okay. Anyone else? We are in time this time. It doesn't happen too often. Otherwise, I'll see you guys next week, huh?
Adios.
Thanks, everyone.
Yeah. Thank you.
Thank you. Bye.
Bye-bye.
Bye.
Thank you. Bye-bye.